This video covers finite state automata. We already saw an example of a finite state dialog manager last week, and now we'll see that these models can be useful for other tasks in natural language processing as well. I'll define the concept, work through a case example of a finite state model that matches a specific regular expression, discuss state transitions, and then move into a discussion of non-deterministic finite state automata. Finite state automata are, at their core, computational models capable of generating regular languages. These languages can be either sequences of subtasks, like what we saw with the earlier finite state dialog manager, or sequences of words or characters, such as with a regular expression. Finite state automata is a plural term, so the singular form is finite state automaton. The key components of a finite state model are an unsurprisingly finite set of states, including but not limited to a starting and end state, and a set of transitions from one state to another. For a given sequence of items, finite state automata work by beginning in the start state. They check to see if the next item in the sequence can be transitioned to according to the rules specified, and if so, they move forward to that state. This process repeats until no transitions are possible, at which time the sequence is either accepted if the state they ended up in is a final state, or rejected if it's not. Finite state automata are often represented graphically, and here's what a graphical representation might look like. Note that for one of the states, Q3, there are two possible transitions, and one of them is a transition back to the same state. The last state, Q4, is the end state, so it's distinguished from the other states here by having a heavier outline. So let's run through what we know about this FSA. We can see that it has 5 states, where Q0 is the start state and Q4 is the final state. We can see that it also has 5 transitions, and we can see that it covers a simple 3-letter alphabet of A, B, and exclamation mark. This finite state model actually matches the regular expression BAA plus exclamation mark, and we can go ahead and work through some test strings to confirm that. We'll start out with the test string ba with 2 A's. So we begin with our sequence at Q0. We see that it's possible for us to transition to the next state, Q1, because the first item in the sequence is a B, and that's a requirement for transitioning to Q1. We then see that it's possible to transition yet again to state Q2, because the next item in the sequence is an A, and that's what's required for our next transition. We're yet again able to transition to the next state, Q3, because the next item in our test string is also an A, and that is, again, what is required to transition to the next state. And then finally, we see that we're able to transition to the final state, Q4, because the next item in our sequence is an exclamation mark, and that's what's required to transition to Q4. This turns out to be the final item in our sequence, so we've reached our stopping point. We find that our stopping point is conveniently located inside a final state, so we can go ahead and accept the sequence. We can go ahead and repeat this entire scenario with a new string, ba ba, to see how that works. We start out pretty much the same way as last time, working through the first few states without a problem. However, at Q3, we suddenly hit an unexpected crossroads. The next item in our sequence is a B, but the only transitions available to us require either an exclamation mark or an A. Unfortunately, this means both paths are closed. Since the state we stopped in is not a final state, this means that this sequence is rejected. So we saw 2 different examples with our finite state model. One was accepted and the other was rejected. Note that more than one FSA can correspond to the same regular language. For example, a test string of ba with 3 A's followed by an exclamation mark could be accepted either by the FSA we just saw in the examples or by a different, slightly stranger FSA where Q2 is the state with multiple possible transitions. When you see people formally define finite state automata, you'll usually see them use the following definition. Basically, a finite state automaton can be specified by enumerating several properties: a set of states Q, a finite alphabet sigma, a start state Q0, a set of final states F and Q, and a transition function between states, delta. The transition function returns a new state Q prime based on the current state and the input sequence element. One thing to note is that by alphabet, the definition you saw in the previous slide doesn't necessarily mean traditional alphabet character. For example, in the FSA you see here, the alphabet would instead be comprised of the words 1, 2, 10, 20, 11, dollars, cents, and so forth. Finite state automata can also have multiple final states. So one thing we haven't covered at all yet is the state transition table. State transition tables are just representations of which transitions are possible, given a current state and a current next sequence item. For example, we could create a state transition table for our original FSA example as follows. We start off with an empty table with the rows corresponding to the current state and the columns corresponding to the next item in the sequence. When we're in Q0 and we see a B, we can transition to Q1, so we add that transition to the table. We can't transition out of Q0 if we see any other items from our alphabet, so we go ahead and add little frowny faces for each of those. Likewise, we can't transition out of Q1 if we see a B. However, we can transition from Q1 to Q2 if we see an A, so we'll go ahead and add that to the table. We finish filling out the Q1 row and move on to the Q2 row. We can transition from Q2 to Q3 if we see an A, so we go ahead and add that to the table. We proceed some more and reach the row for Q3. We can transition from Q3 back to itself, Q3, if we see an A, so we go ahead and add that to the table. We can transition from Q3 to Q4 if we see an exclamation mark, so we go ahead and add that to our table as well. We can't transition to any other state from Q4, but if we reach the end of the sequence, we will be in an accept state, so we can go ahead and put a little smiley face there, since that would mean we would accept the sequence. State transition tables basically just make it easier to determine whether your input will be accepted by the FSA, because it reduces the process to just consulting a table and following its instructions. Here's the formal algorithm of what that would look like. We initialize the sequence index to the beginning of the sequence and initialize the current state to the model's initial state. We then enter a loop where we have a few possibilities that determine the next action. If we've reached the end of our sequence and the current state is an accept state, we can accept the sequence. Otherwise, we can reject it. If we're not at the end of the sequence, but there are no possible transitions given the state and sequence element we're currently at, we can reject the sequence. Otherwise, we can update the current state to be whatever state is output by our transition table, given the present information. Then we increment our sequence index and go back to the beginning of the loop. So far, we've seen examples of both deterministic and non-deterministic finite state automata. We just haven't attached those labels to them. A deterministic finite state automaton is one for which at each point in processing a sequence, there is one specific action that can be taken. On the other hand, a non-deterministic finite state automaton is one for which, at one or more points in processing a sequence, there are multiple permissible next steps. So, given this information, is the top FSA deterministic or non-deterministic? It turns out that it's deterministic because even though Q3 has multiple transitions leading out of it, both transitions are attached to different members of the alphabet. So if the next item in the sequence is an exclamation mark, one path will be taken, whereas if the next item in the sequence is an A different path will be taken. So what about the bottom model? The FSA on the bottom is actually non-deterministic because there are multiple transitions leading out of Q2, and both of them are attached to the same alphabet member. This means that if the next item in the sequence is, in this case, an A, there are multiple valid paths that can be taken. Deterministic and non-deterministic FSAs have some interesting properties, and both are equally powerful. In fact, every non-deterministic FSA can be converted to a deterministic FSA. However, non-deterministic FSAs are a bit harder to check for input acceptance, so there are basically two approaches for doing so. In one, you convert the non-deterministic FSA to a deterministic FSA, and then check that version, and in the other, you manage the process as a state space search. If you end up going with the latter approach, there are several assumptions that are made. First, this approach assumes that there is at least one path through the FSA for any item that is part of the language defined by the machine. And second, it assumes that not all paths through the FSA for an accept item will lead to an accept state. And then third, it assumes that no paths through the FSA lead to an accept state for an item that is not in the language defined by the machine. Overall, the search succeeds if any path is found for a given item that ends in an accept. The search fails if all possible paths for a given item lead to failure. So we could determine whether the search for a sample string ba with 3 A's is successful as follows. We begin by iterating through the model as normal, with all going smoothly. However, pretty soon we need to transition out of Q2, and there are two possible ways to do so given our current position in the input sequence. We choose one of the paths randomly, and it ends up being a bad choice. Since we're stuck in Q3, this path fails to reach the accept state. We return to the point of initial confusion where there were two possible paths that could be taken and decide to transition back into Q2 instead of moving on to Q3. We have to make another decision with the next item in the sequence because it's also an A, so this time we go ahead and transition onward to Q3. This time we're successfully able to transition to Q4. So even though all possible paths didn't end in an accept state, at least one of them did. This means that the test input should be accepted. A few final notes about non-deterministic FSA search. In this search space, states are pairings of FSA states and sequence indices. We need to keep track of which search space states have been explored, and by doing this, we can systematically explore all paths through an FSA given a sample input. And finally, one additional interesting property of finite state automata in general is that they're compositional. You can apply set operations like union, concatenation, negation, and intersection to them. To do so, you might need to utilize a special type of transition called an epsilon transition. An epsilon transition allows you to move from one state to another without consuming an item from your input sequence. So we covered a lot of things in this video. We saw that finite state automata are computational models that describe regular languages, and you can process test sequences in order from start to finish to determine whether they're members of those languages. You can represent state transitions and FSAs using state transition tables, and FSAs can be either deterministic or non-deterministic. They're also compositional, so you can apply set operations to them. Finite state automata are useful for a variety of tasks in natural language processing. We've already seen two in this course, managing dialogue and testing regular expressions. They're a versatile model that is easy to implement and easy to interpret.